Conditional probability with non-equally likely outcomes. Welcome, everyone. Today, we are moving into a more advanced area of probability. Up until now, in our previous lessons, we have mostly focused on scenarios where every outcome was equally likely. Think of a fair six-sided die where every number has the exact same chance of appearing. However, as we move into more complex, real-world applications, we often encounter situations where outcomes are not equally likely. In these cases, different outcomes carry different weights or different levels of probability. To begin, let's look at how we understand these non-equally likely outcomes. When the outcomes aren't uniform, we can no longer rely on simply counting the number of favorable outcomes and dividing by the total. Instead, we must use the general probability of events. The good news is that the formal definition of conditional probability remains exactly the same as what you have already learned. Specifically, the probability of event E, given that event F has occurred, is equal to the probability of the intersection of E and F, divided by the probability of F, provided that the probability of F is not equal to 0. Because we aren't just counting outcomes anymore, your main task here will be to carefully calculate the probability of the intersection, which is the probability of both E and F happening, as well as the probability of the condition, F, based on the specific probabilities provided in the problem. Later in this session, I will show you a visual tool called a tree diagram that will make calculating these specific probabilities much more intuitive. The tree diagram, a visual tool. Now that we've established that we can't always rely on simple counting when outcomes have different weights, I want to introduce you to a powerful visual tool that will make these complex problems much easier to manage: the tree diagram. Tree diagrams are incredibly useful when we are dealing with multi-stage experiments. That is, scenarios where one event happens and then another event follows it, often depending on what happened in the first step. Let me walk you through how a tree diagram actually works. First, you'll see points called nodes. These represent your starting points, your decisions, or the random events occurring at each stage. From these nodes, we draw branches. Each branch represents a possible outcome for that specific stage of the experiment. To keep track of the probabilities we discussed in the previous slide, we label each individual branch with its specific probability. Now, here is the most important rule to remember for your calculations. To find the probability of a specific sequence of events happening one after another, you must multiply the probabilities along that particular path. In the next slide, we are going to put this exact method into practice, using a two-bag experiment to see how these branches and multiplications work in a real-world calculation. Real-world example: the two-bag experiment. Now that we understand the theory behind non-equally likely outcomes, let's put it into practice with a concrete example. This is where the concept really comes to life. Take a look at this scenario. Imagine we have two different bags. Bag 1 contains 3 red balls and 2 blue balls. Bag 2 is a bit different. It contains 4 red balls and 6 blue balls. Now, here is the crucial part where we move away from equally likely outcomes. We don't just pick a ball. First, we choose a bag at another random, meaning there is a 50-50 chance or a probability of 0.5 for each bag. Once a bag is selected, we draw exactly one ball from it. To solve a problem like this, we need to be very organized, so let's walk through a step-by-step solution. In step 1, we must clearly define our events so we don't get confused later. Let's use B sub 1 to represent choosing bag 1, B sub 2 for bag 2, and a capital R to represent the event where the ball drawn is red. Moving to step 2, let's identify the probabilities we already know from the scenario. Since the bags are chosen at random, the probability of B sub 1 is 0.5, and the probability of B sub R2 is also 0.5. Now, look at the contents of the bags to find our conditional probabilities. For bag 1, the probability of drawing a red ball, written as the probability of R given B sub 1, is 3/5, which is 0.6. For bag 2, the probability of R given B sub 2 is 4/10, which simplifies to 0.4. In step 3, we apply the visual tool we discussed in the previous slide, the tree diagram. Imagine starting at a single root point. First, you branch out into two paths, one for b sub 1 with a probability of 0.5 and one for b sub 2, also with a probability of 0.5. From the b sub 1 branch, you split again into red with a probability of 0.6 or blue with a probability of 0.4. Similarly, from the b sub 2 branch, you split into red with a probability of 0.4 or blue with a probability of 0.6. Now, in step 4, we need to find the intersection, which is the probability of both choosing bag 1 and drawing a red ball. To do this, we multiply along the path the probability of b sub 1 times the probability of r given b sub 1. That is 0.5 times 0.6, which gives us 0.3. In step 5, we need to find the total probability of drawing a red ball, which we call the probability of r. To get this, we must account for all paths that end in a red ball. We add the probability of getting a red ball from bag 1 to the probability of getting a red ball from bag 2. Calculating this, we take 0.3 from the first path and add it to the second path, which is 0.5 times 0.4, or 0.2. So 0.3 plus 0.2 equals a total probability of 0.5. Finally, in step 6, we use the formal definition of conditional probability we learned on the first slide. Let's say we want to find the probability that we chose bag 1, given that we already know the ball drawn is red. This is written as the probability of b sub 1 given r. To find this, we take the intersection we calculated in step 4, the probability of b sub 1 and r, and divide it by the total probability of r that we found in step 5. That gives us 0.3 divided by 0.5, which simplifies to 3/5, or 0.6. As we move to the next slide, pay close attention, because I will highlight some common pitfalls where students often trip up during these specific calculations. Common mistakes to avoid. First, a very frequent mistake is confusing the probability of a given b with the probability of b given a in our previous example. Look at the difference between p of r given b1 and p of b1 given r. The first one, p of r given b1, is the probability of drawing a red ball, assuming we already know we are looking at bag 1. However, p of b1 given r is something entirely different. It is the probability that we chose bag 1, given that we have already seen a red ball. To avoid this, always carefully identify which event is the given condition, the event that has already occurred. Second, be careful with your arithmetic operations when using tree diagrams. A common error is adding probabilities along a single path instead of multiplying them. Remember this rule: you must multiply probabilities as you move from the start to the end of a single outcome path to find the intersection. You only use addition when you are combining different, separate paths that lead to the same final result, such as when we added the two different ways to get a red ball to find the total probability of r. Finally, do not forget the denominator. When calculating conditional probability, it is easy to find the intersection, but you must remember to divide by the probability of the condition, which is p of f. If you forget to divide by the probability of the event that has already happened, your final answer will not be a true conditional probability. Now that we have worked through the two-bag example, I want to pause and discuss some common pitfalls. Even when you understand the logic, it is very easy to make small errors that change your entire result. Keep these points in mind as we move into our final summary of the lesson. Key takeaways. First, remember that the fundamental formula for conditional probability, where the probability of event E given event F equals the probability of the intersection of E and F divided by the probability of F, is a universal tool. It remains valid for all distributions, whether the outcomes are equally likely or not. Second, when you are faced with multi-stage experiments, like the two-bag experiment we just worked through, tree diagrams are essential. They serve as your primary visual tool to track the flow of events from start to finish. Third, pay close attention to your operations. When you are moving along the branches of a tree diagram to find the probability of a specific sequence or intersection, you must multiply the probabilities along those paths. Finally, if you need to find the total probability of an event occurring across different scenarios, you should sum the probabilities of all the individual paths that lead to that specific final result. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of this topic. Keep these principles in mind, and you'll be able to navigate even the most complex probability problems with confidence.